Swayam Prabha. Digital India. Educated India.
Good afternoon everyone, and today we will be continuing with module 6, which is micro texture measurement using electron backscatter diffraction technique in a scanning electron microscope, that is SEM. So, this is lecture number 30, and in which we will understand Kikuchi diffraction pattern, and this is part 1. So, the concepts that will be covered in this lecture are convergent beam electron diffraction in TEM, which is this one, right. Just let me get the laser pointer, and then the second is defect and excess Kikuchi lines. The third is electron backscatter diffraction in a scanning electron microscope. A brief, very brief information regarding the microcosal and selected area channeling techniques in SEM, and finally, the difference in Kikuchi pattern that formed in TEM and SEM EBSD. So, in order to obtain crystallographic information, that is the information regarding the orientation, that is the information regarding microtexture from a TEM or from a SEM, that is EBSD we know, and in case of TEM, that is convergent beam electron diffraction technique. We are mostly concerned with the formation of the Kikuchi pattern. So, how the Kikuchi pattern can be developed and how it can be obtained properly. Then second is identification of this obtained Kikuchi pattern. So, we need to identify the crystallographic indices pertaining to the Kikuchi bands and the angle between the bands in form of zone axis, right. So, we need to understand the crystallographic indices of the bands and the poles and lines of the Kikuchi pattern, its relationship with the sample reference system. So, when we are putting the sample in the TEM or in the SEM, what we are trying to do, we are putting the sample with knowing its specific important reference systems, means RD, TD and ND, for example, for a rolled specimen. So, if we can do that, if we can put the specimen in such a way that we know which direction is RD, which direction is TD and which direction is ND, then we can get the relative position of the bands and the poles with respect to this external reference direction. So, what basically is done is that for a certain position. So, you see the electron beam is a very thin beam, it has a very small diameter. So, it falls on a very small area of a nanometer size. So, the beam is few nanometer diameter and it falls on that area and it irradiates it and makes a interaction volume, right, a very small interaction volume. So, from a very small sample volume in a polycrystalline material, the position which is definitely a single crystal because of the size of the sample volume, because of the cross section of the electron beam and the interaction volume, a Kikuchi pattern is obtained from that position, and then that Kikuchi pattern is basically analyzed to obtain the, as I said, the relative positions of the bands and the poles with respect to the reference directions, and it is basically from those bands and poles identification of the crystallographic planes with respect to this RD, TD and ND is obtained. And then the the electron beam is rastered. So, it is taken to the next step and then the same process is continued. So, another Kikuchi band pattern is taken and then it is shifted again and another beam falls on the side of from the other. So, scanning of the whole sample volume, first it is scanned like this 1, 2, 3, 4, 5, 6, and then it goes to the next step 1, 2, 3, 4, and then the whole area is scanned to obtain Kikuchi pattern from that whole area, which may differ in some cases and which may differ, which may not differ in some other cases. So, you see the electron beam is basically rastered on a subjected small sample area to obtain the information of the microstructure like this. So, if we go deeper, so how a Kikuchi band is produced. So, in case of the convergent beam electron diffraction in a transmission electron microscope, when the incident electron beam falls on a sample, a very thin sample, and you know that the sample of a TEM is made in such a way that it is basically a round sample and it is basically thinner at the center and little thicker at the sides. So, it is prepared in such a way that at the thin position one can get diffraction spot, and one can go to the thicker and thicker position to see that whether Kikuchi bands can be obtained because of multiple scattering. So, what is the technique that in that thin specimen a little thicker place is chosen, and then the incident electron beam basically falls on the specimen. And when this electron beam falls on the specimen, it starts to scatter. So, you see it interacts, the electrons interacts with the atoms and it starts to scatter, and when it starts to scatter, it scatters in all possible directions, right. So, you see when the scattering is one time, then it is elastic scattering, right, as I said in the last class, and when it starts to occur on multiple time, it becomes inelastic scattering. And how it is? It is such that in every time the material, the electron is scattering with when it interacts with the nucleus or the electron, it loses a very little amount of energy, and it is elastic scattering when the lost energy is not detectable. But when it interacts a lot of time, multiple times with the electrons and the nucleus many times, then the loss of energy become considerable and the scattering becomes inelastic. We also know that when with the increase in the multiple times of interaction, with the increase in the number of interaction, the the scattering angle also increases, and as the scattering angle increases, we also know that the intensity of the beam basically reduces. So, you see that when the incident beam basically falls on the specimen and it interacts with atoms which are in periodic arrangement, and so it interacts with atoms multiple times, and when it scatters multiple times, it happens as if that the electron beam is coming from inside of the specimen, and it is coming in all possible direction. How it is that one electron beam is falling and then it is scattered one time. So, say for example, it goes in this direction and then it is scattered another time and it goes like this direction. Now, multiple electrons are falling in the from the electron beam, and they scatter multiple times using a lot of millions of atoms present in the metal. And so, the scattering basically takes place in all possible direction at 360 degrees in the space, and therefore, the electron seems to come at all possible angles from inside the sample. And now, when this kind of multiple scattering takes place, this scattering becomes inelastic, and the angle at which it is scattering, it decides the intensity of the beam. So, higher the angle of scattering, larger multiple times the scattering has taken place, and therefore, the angle is higher and the intensity of the beam is lower. Now, when such inelastic scattering takes place and the beam seems to come out in all possible direction from inside the sample, then if a final scattering takes place, that scattering, because it is a single scattering, will be an elastic scattering, and when this scattering takes place, and because of the periodic arrangement of the various of the atoms, the various HKL planes can lead to reinforced scattering, which is basically diffraction, and this diffraction occurs as if in a kind of a locus of point, like like a Cosel cone. So, the diffraction, say for example, from a certain HKL plane may occur in all possible way in order to form a cone, something like that, and it happens in all possible direction following the Bragg's law. Now, as you know that because the electron beam has a very small lambda. Now, because it has a very small lambda, the Bragg's law is relaxed, and because of which a certain HKL plane can diffract from both the direction, right. And as the electron beams seems to be coming from inside the specimen and in all possible direction, the diffraction following the reinforced scattering following Bragg's law, that is the diffraction, occurs from both the side of a single HKL plane, and it forms a locus of point which makes a cone like that in both the direction. These cones are basically known as Cosel cones, right. And like in this example, we have shown it for a single HKL plane which is diffracting to form a Cosel cone. All possible HKL planes basically diffracts. Now, under such situation, what happens that these Cosel cones, which are basically diffraction at Bragg's angle theta for a certain HKL plane. So, theta b for a certain HKL planes, when these Cosel cones, you see, if its size increases, because it is a ray, right, it will spread out, right. So, when it spreads out and falls on the phosphor screen, which is just placed below the incident beam and the sample. So, when it falls on the phosphor screen, it forms two lines, and these lines are basically, you see, the angle between these two lines are basically 2 theta. So, if we make a bisector of this line, which is basically parallel to the HKL plane, then it becomes theta, and this one also theta, right. So, theta plus theta is 2 theta. Now, these Cosel cones when falls on the phosphor screen, because of the because the angle of diffraction is so small, as the lambda is so small for an electron beam, for each and every HKL plane, the Cosel cones when it falls on the phosphor screen, it forms straight lines like this. So, you see that in this way Kikuchi lines can be obtained from TEM using convergent beam electron diffraction. Now, when the incident electron beam falls on the specimen, the incident beam is slightly tilted, it is called rocking of the incident beam. The rocking actually takes place at a very small theta, so that the electrons that are generated in the inside the material by the method of multiple scattering or inelastic scattering seems to come from all possible direction, and such that a proper Kikuchi pattern or a proper Cosel cone can be obtained, from which the Kikuchi pattern can be formed. Now, you see that here is a little detail of how the Kikuchi pattern basically develops in case of the convergent beam electron diffraction inside the TEM. You see, when the electron beam falls on the specimen, and as I said that the direction of the electron beam is it is falling. So, it is slightly rocked. So, it changes. So, this is known as the rocking of electron beam at a given sample site. So, as the electron beam is falling on the specimen, it is slightly rocked, and you see multiple scattering takes place. These red arrows are shown, which shows that multiple scattering takes place in the specimen. And as I said that as the number of scattering increases, the angle of scattering basically increases. So, as for a small number of scattering, that is phi e, the angle is less, right, and the intensity of this beam which seems to be come from inside the specimen is basically you see higher, right. And when for a certain HKL plane, this electron beam basically comes and diffracts, finally, final elastic scattering, which is reinforced scattering following the Bragg's law happens, then this incident beam falls here and it diffracts and goes to the outer position of the Kikuchi band. Now, on the other hand, when the number of scattering that is increased, then the inelastic scattered inelastically scattered electrons has lower energy and it has an angle that is phi d which is greater than phi e. So, when it falls on the same HKL plane, it falls like this and it scatters inside, that is reinforced scattering following Bragg's law, that is diffraction following a particular theta b for a certain HKL plane. For the same HKL plane in this case, this beam has a lower intensity when it falls here. So, what happens that while the incident electron beam also falls straight on the screen because the specimen is so thin, it is almost electron transparent, and so it falls on the screen, the intensity of this electron beam which is diffracted and falling here will be lower, and the electron beam which is diffracting and falling here will be little higher, leading to form a Kikuchi band. You see, Kikuchis are basically two lines which are forming. One line is inside near to the incident beam and another line is outside. So, the outside line becomes excess, it is called the excess Kikuchi line because it is brighter, and the inside line is called the defect Kikuchi line because it is basically darker because its intensity is lower. So, you see like that we can in convergent beam electron diffraction in a TEM we will obtain each Kikuchi bands with a excess Kikuchi line and a defect Kikuchi line. So, the excess Kikuchi line will be outside and the defect Kikuchi line will be inside for each and every HKL plane, right. And therefore, you see that when such a situation arises, then what happens that the if I explain in a little detail that, as I said, that this electron beam which is diffracted and coming inside forms a low intensity line which is defect line, and the beam, this beam which has a high intensity diffracted outside to form a high intensity excess line, both basically satisfies the Bragg's law. So, if we look here in the figures on the left side, if there is no sample present or the sample is present in the thinner position where there is no Kikuchi formation, then the intensity of the incident electron beam falling on the the surface of the phosphor screen will look something like this. But you see that once this Kikuchi bands starts to form, say for example, for a certain HKL plane if we show, and then the excess line and the defect line generates, then what is basically happening is that the intensity which is present here, which has to be here, now because of the diffraction is going and falling here, whereas the intensity which usually will fall here without the Kikuchi diffraction will go and fall somewhere here, form somewhere here. So, you see that because of such a phenomena, the intensity of the direct incident beam reduces in one case and increases in the other case for one Kikuchi line and another Kikuchi line for a Kikuchi band to form such kind of excess defect Kikuchi lines for in each and every HKL plane. So, here we are showing the figure. This figure has been adopted from the figure present in Introduction of Texture Analysis book of Olaf Engler and Valerie Randall, and you can see what I was trying to explain you is that here is for example, a band, right. This is a Kikuchi band out of many Kikuchi bands. So, this is another Kikuchi band, this is another Kikuchi band that has formed, and if you look, the inside band, inside line of the band is darker, right, and you see for this band also the inside line is darker. You see for every band the inside line is darker, the inside line is darker, and if you look at the outside line is basically brighter. The outside line you see for this Kikuchi band also and for this Kikuchi band also is basically brighter. So, when the incident electron beam falls on a very thin specimen, from where we can obtain Kikuchi band, means from the thicker part of the thin specimen, and then the direct incident beam falls, making a very bright area on the phosphor screen. However, when excess and defect lines arises because of the diffraction formation of the causal cones and formation of Kikuchi pattern, the diffraction pattern basically looks like this. And when, if we know that how we have put the sample inside the TEM, and if we know the RD, TD and ND, then one can relate these lines or bands with respect to the RD, TD and ND in order to obtain the information of the orientation of that particular position of the sample, right. So, as I said that if we look into the Bragg's law, and we have learned this in the last class also, that n lambda is equal to 2d sin theta, but as the sin theta, as the theta is so small, because the lambda is also so small for the electron beam, we can say that n lambda is equal to 2d theta. So, theta is basically n lambda by 2d, which is so small, and therefore, what happens that because of this small theta, which is in 10 to the power minus 2 radians or something, the apex angles of these causal cones, you see we form these causal cones, right, cones like this, it comes like this from a single HKL plane, and the apex angle is almost close to 180 degrees. So, the causal cones are almost flat, and so that the recorded Kikuchi pattern, you see Kikuchi pattern on the phosphor screen. So, each band of the Kikuchi pattern on the phosphor screen seems to be a pair of parallel line, and if the distance of the sample and the phosphor screen is properly calibrated, then the thickness of these bands, each of these bands could be related to 2 theta b, right, because but a proper calibration is needed, and once it is calibrated, we know that we can relate each thickness to 2 theta b. So, this is 2 theta b for a certain HKL plane, and this is another 2 theta b for another HKL plane. So, from the thickness of the band, one can find out which HKL plane it is coming from, because from this formulation 2 theta b basically is inversely proportional to d HKL, right. So, it is inversely proportional to the lattice spacing of the planes, right. So, we have discussed, but to brief it, the pair of parallel lines are basically known as bands. The intersection of bands are basically zone axis, and in certain case when there are several bands intersecting at the same point, it could be a major zone axis, right. So, the whole Kikuchi pattern basically consists of pairs of parallel lines, right, where each pairs of lines has a distinctive width 2 theta b corresponding to this crystallographic plane. So, is proportional to 1 by d HKL. Then the Kikuchi pattern therefore, essentially embodies the angular relationship in the crystals. So, both interzonal and interplanar, and hence it can implicitly contain the crystal symmetry of the material. So, this has the crystal symmetry of the material and can give the information of the crystallographic texture of the material if R d, T d and N d of this sample which is put in the TEM is known. In case of scanning electron microscope, the process of doing or observing or obtaining this Kikuchi pattern is known as electron backscatter diffraction. Now, as I have said in the previous lectures that there are elastically backscattered electron and elastically scattered in the front side in case of TEM, right. So, say for example, there could be inelastically backscattering and then finally, it could be diffracting. So, you see that when the electrons basically interact with the nucleus, or if we can get elastically backscattered electron, but if we can tilt the sample and if you can tilt the sample at say for example, at a certain degree say 60 degrees to 80 degrees something like this. So, when the electron beam basically falls on the sample and once it falls on the sample by the same phenomena as I explained in case of convergent beam electron diffraction in the TEM, when the electron beam falls on the sample, elastic scattering takes place if the scattering is less number of times, right, when it is the loss of energy is not detectable, and inelastic scattering takes place when it scatters a multiple amount of time, and so there is a loss of energy of the electron. So, while multiple scattering takes place in the sample near the surface at the interaction volume for a certain small part where the electron beam is falling. As I said that electron beam has a diameter of few nanometers. Now, you see when multiple time scattering occurs while the sample is tilted like this, it seems that the scattering is making the electron to come out in all possible direction in the space as if the electron source is inside the sample. So, it seems that the electron source is somewhere here from where the electron is basically coming out in all the direction like this. And when such a situation occurs, then what happens that if the electron comes out after the final scattering and if it is a reinforced scattering because of the presence of periodic lattice arrangement of the crystal of the atoms. Now, what happens that in this case also say for example, many electrons are coming on the above direction and few are coming in the lower direction and it is throughout, and then each of this inelastically scattered electron basically finally diffract to form a locus of a cone, right, a locus of a cone same like the one which we observed in the TEM, but you see in this case also for a different geometry, right. And this locus of the cone for a certain HKL plane can be observed in a phosphor screen which is not present below the incident beam, but present at 90 degree away from the electron beam, right. So, it is present at a different position from the electron beam. So, in this case also the causal cones have a very small apex angle, and thereby what happens that when the electron which is finally diffracted falls on the phosphor screen forms Kikuchi lines, and here also a band contains two lines and the angle between the bands could be related to 2 theta, right, and it forms like this. So, this is a figure which is obtained from the book of Olaf Engler and Valerie Randall, Introduction to Texture Analysis, and you can see that for different HKL planes one can obtain different bands, right, and these bands are forming, each band has a different thickness and therefore, it can be related to the 2 theta b means the 2 times of the Bragg angle, and thereby it could be related to a certain HKL plane. So, if the sample is placed in such a way that the R d, T d and N d, that is the important sample reference direction is known, then one can relate and find out these crystallographic planes and then relate it to the sample reference direction to find out the orientation. So, in EBSD diffraction occurs from the interaction of primary backscattered electrons with the lattice planes which are close to the specimen surface, right. So, in case of TEM you see it is a transmitted electron which gives the Kikuchi pattern, and in case of the electron backscatter diffraction, that is EBSD, it is in the reflection geometry, right, to obtain the Kikuchi pattern. And you see in this case the planes which are somewhat like this will be irradiated, and therefore, you see each and every plane will be irradiated which are in parallel to this direction, almost parallel to this direction. Each and every plane will produce an Kikuchi line or Kikuchi belts. So, you see that in case of EBSD, why it is important to observe EBSD than the TEM, because you see in case of TEM the sample preparation is extremely tough. In case of TEM, to raster the sample in a large amount is also difficult, and texture is also related to statistics. Even if it is micro texture, a large number of grains needed to be scanned to get sufficient information for the confidence of the researcher or the scientist who is working, that the information generated is quite representative. So, in case of EBSD what happens, thicker samples can be used to do EBSD. So, the sample preparation becomes much easier, and therefore, EBSD is a more known and understood technique, though its geometry is complicated, because you see its geometry is complicated because the sample is rotated at a certain angle, and one can rotate at various alpha. 70 degree is mostly preferred, because at this angle the electron beams Kikuchi pattern can be obtained in a phosphor screen which is present now vertical with the sample. You can see that if this is the incident beam and perpendicular to the incident beam is not somewhere which is parallel to the one which is representing a major zone axis of the specimen, but it is some, and it is not even at the center of the phosphor screen, but it is relatively at certainly at the top position, somewhere at the top position, right. So, what I mean to say is, in this case the camera or the phosphor screen is presented at 90 degree away from the path of the electron beam, and this is not a simple geometric relationship as in the TEM. So, complicated mathematical expressions will be needed to solve the Kikuchi pattern to obtain the HKL planes and to relate it to the RDTD and ND of the sample. Of course, this will be, but it can be done using a software. Now, what happens that why we do the tilting? If we do the tilting at 70 degree, it helps to the electron beam to diffract, and it goes directly to the detector which is placed at vertical in this case. Now, in case of EBSD, the distances of the pattern cannot be transformed into angles by simple relationship, and that is what I said earlier because of the complex geometry. The incident electron beam or the beam normal lies, you see the incident electron beam or the beam normal, and this is the same thing B n actually lies out of plane of the the phosphor screen. So, the phosphor screen is here, and in case of TEM it used to be here. So, therefore, you see because the phosphor screen is 90 degree away, it is vertical now, it is out of the line of the electron beam. Now, in case of EBSD there will be no excess or defect lines, right. So, in this case you will have no excess or defect lines, and that is what we should I should have said in the last slides also. Now, in order to evaluate this Kikuchi pattern and to raster the whole microstructure, a part of the microstructure sampled area, and to obtain multiple millions of Kikuchi pattern for a small area of the sample, and then to obtain the texture a dedicated software is required, right. So, what is the advantage here? The EBSD pattern that is obtained in SEM has a much larger steric angle, nearly 5 times larger than what is obtained in case of convergent beam electron diffraction in a TEM. So, what happens is that it allows a large portion of the gnomonic projection to be surveyed in one pattern, and therefore, it becomes easier for indexing. So, you see what is the difference between the Kikuchi pattern that is obtained from the transmission electron microscope, and what is it different from the scanning electron microscope in EBSD. So, you see in case of EBSD, a large steric angle nearly 5 times can be obtained as compared to the TEM case, right. However, in case of TEM, the Kikuchi patterns are sharper and more prominent than that of the EBSD. In case of TEM, there is a presence of defect lines and excess lines. In case of EBSD, there is no defect lines or excess line, they have equally dark intensities in both the lines, right. Now, the angular precision of TEM is very high, that is 0.1 degree to 0.5 degree. In case of SEM, the angular precision is low, that is nearly 2 degrees in most of the cases. So, there are other techniques in SEM that can be used to obtain Kikuchi patterns or to obtain orientation relationship with respect to the specimen, and one of the technique that I would like to mention in a very brief, that it is micro Kossel technique, and this is Kossel in 1935 who basically showed this. And you see, in this case electron beams actually falls on the sample, and the X-ray diffraction is basically taken, because you see electrons falls on the sample produces diffracted X-rays also, and these diffracted X-rays are basically used to understand the orientation relationship of the material, and this diffracted X-ray beams comes from inside the sample. On the other hand, another important technique, selected area channeling is one of the technique, where the sample in the SEM is not tilted, it is kept flat like that of the TEM. In this case, what happens that the electron channeling diffraction takes place in the SEM, and the Kikuchi pattern and the electron beam falls, and the backscatter diffraction takes place like this, and there is a detector on the top along with the electron gun, and the Kikuchi patterns are obtained on that phosphor screen. And but you see the Kikuchi pattern that is obtained has a very small steric angle. So, in this case also the incident beam has to be rocked. So, rocking of electron beam at the sample site is done, so that the electron comes out in all possible directions in order to get the final reinforced scattering. So, these are two techniques which are basically not used for nowadays to do this orientation or micro texture measurement. So, what we can conclude from this today's lecture is, you see, convergent electron diffraction in TEM is used in such a way that the electron beam is basically rocked while it falls on the sample, and it interacts with the atom in the periodic lattice arrangement of the sample, and it scatters in all possible direction. So, the scattered electron source seems to be coming from inside the sample, right, and these electrons undergo a final elastic scattering, and this elastic scattering actually will be reinforced scattering. That means, it will follow the Bragg's law and it will diffract because of the periodic arrangement of the atoms, and this strong reinforced scattering will occur for every set of HKL planes, right. Now, since the electrons are coming from all possible direction, the diffraction following the Bragg's law will also occur in all possible direction, but following Bragg's law. right. So, the diffraction will form a locus of diffracted electron beams, which is like a surface of a cone, and it is called a Cosel cone, right. The Cosel cones basically falls on the phosphor screen to form the Kikuchi pattern. Now, the beam is basically rastered one after another. So, it scanned the whole small sample area to obtain the Kikuchi pattern of the sampled area that we have decided. Now, in case of EBSD, Kikuchi pattern is obtained from a thick specimen, which is easier to the sample preparation of thick specimen is much easier as compared to the TEM sample preparation. The thick specimen is basically tilted and the detector is now vertical instead of horizontal detector, which is now away from the electron beam. So, you see, in this case also Kikuchi bands can be obtained, but with a lower angular precision. Now, because of this difference in the arrangement, in case of TEM, excess and defect patterns are observed. In case of EBSD, no such excess or defect lines are observed. That is all for today's class. Thank you very much.